Today we'll start with session 5, that is simple problems from session 1 to session 4. So as you know, this unit is simple stresses and strains. From session 1 to 4, we have covered a lot of concepts and some basic definitions related to the stress and strains. So we have seen the different first definition of stress. Stress is internal resistance set up in a material per unit cross-sectional area, right? So then that again, we have seen different types of loads, different types of stresses and strains and their respective formulae, and what is the mathematical representation of that. And later on, we have seen the Hooke's law. Hooke's law states that the stress is directly proportional to the strain with an elastic limit. So then again, we have introduced a constant in the Hooke's law. That constant is called as E. So that E is called as Young's modulus, right? So then later on, there we have seen different types of elastic constants. That is Young's modulus. That is also called as modulus of elasticity. And next we have seen the modulus of rigidity or rigidity modulus, and it is represented by letter C or G. And next bulk modulus, that is represented by letter K. Then later on we have write a relation between these three elastic constants, right? So then we have seen the Poissons ratio. Poissons ratio is defined as it is the lateral strain by longitudinal strain. So the how this lateral strain varies with respect to longitudinal strain, then we arrived an equation there that is represented by a mu, nu, or 1 by m. So this is the Poissons ratio. So then later on we have seen the stress strain curve for ductile materials. The example we have taken as a steel material there. Then that steel material we have prepared the specimen. So as per the standard, the specimen is prepared and that is tested in the tensile testing machine, right? So in the tensile testing machine, what happens there? The specimen is held in two jaws. One is upper jaw and lower jaws. Then we keeps on applying the load. So the gradually we apply the load and we observe what the changes takes place in the material in the tensile testing machine. So that readings we have taken it from the tensile testing machine. So that we drawn the stress strain curve. So on the x-axis we have taken the strain, on the y-axis we have marked the stress. So at the initial point, that is O, then on the stress we have marked the points A, B, C, D, E, F, and by connecting these points we have drawn the stress strain curve. So at the point A up to from point O to A, so that point A is called as limit of proportionality. So from O to A, that is called as limit of proportionality, means stress is proportional to the strain. Again from the B is called as elastic limit. So elastic limit means so up to that limit the material regains its original shape and size. So after removal of the load, so that varies up to the point that holds good up to the point B. So because of that it is called as elastic point. So up to the point B, the elasticity holds good. Elasticity means it is the property of a material by virtue of which it regains its original shape and size. It regains its original shape and size. So that is called as elasticity property. So that point we call it as the elastic limit. So the after that you note down while testing the specimen in the tensile testing. So initially we need to give more load, but there is a small change in the strain. But later stages, when you give the small change of load, gives you the the more change in the strain. So then again there is the point C. So that point C we call it as the upper yield point. So upper yield point means up to that point there is a small change in the load, again there is a small change in the strain, that is called as upper yield point. Then the lower yield point means load if decreases, the even load decreases, then again there is a change in the strain. So that comes to a point up to the D, that D point is called as lower yield point, right? So that upper yield point and lower yield point, these points changes with respect to the material. right? Then next, after the point D, if you keeps on applying load again, then it reaches the point E. That point E is called as ultimate point. The ultimate point means ultimate stress. Ultimate stress means the maximum load the material can withstand. So that point, so how much maximum load the material withstands. So when you calculate the stress by taking that maximum load, then that stress we call it as ultimate stress. So after that, again, if you start applying load, means again there is a starts decreasing in the load again also, but there is the measurable change in the strain. There's a lot of change in the strain takes place. So there is in the specimen, there's a neck formation takes place. When it reaches point F, then the material going to fail. So that point we call it as fracture point. So then this is how we have drawn the stress strain curve. Then again we have studied different types of stresses and how to calculate those stresses. We have seen the formula also in the previous session, right? And the later on in that session, third session, in the fourth session, we have seen the percentage of elongation and percentage reduction in area. So during the testing of the material, the tensile testing, the length increases and the cross-sectional area decreases. So there, if the length increases, then there is a change in the length. So then the original length. So by considering this, if you calculate there, we are arriving the percentage elongation. Then there is a percentage reduction in area because area is reduced. When the length increases, area reduced. So initially the original area you calculate, then after breaking, what is the area you calculate. So based on those two areas, if you calculate the reduction in area, that too in percentage, so that these two are very important, right? So now in this session 5, we will solve some more problems on the topics covered from session 1 to session 4. So this is the first problem. A steel bar 2.4 meter long and 30 mm square is elongated by a load 400 kilonewton. If Poissons ratio is 0.25, find the increase in the volume. Assume E is equal to 200 kilonewton per mm square. First read the problem carefully and note it down of what is given in the problem. What he has given in the problem and what he has been asking. So these two are very important. So right. So now I am writing it as given data. So this given data means I am noting it down from the problem given. The length of the steel bar he has given, that is 2.4 meter. 2.4 meter. So the unit is in meter. I need to convert this meter into mm because the 30 mm square he has given. So the length is in meter, but the square side he is given it in mm. So either you convert meter into mm or mm into meter. So all the units should be in 1 units. So now I am converting this length itself into mm. So I am multiplying this with 1000. So it becomes in mm. So now B is equal to T is equal to 30 mm. It means 30 mm square he has given. It means if this is a square, so then this side is T and this is B. If B and T both are equal, B ಮತ್ತು T ಎರಡು equal ಆದಾಗ ಮಾತ್ರ ಇದೇನಾಗುತ್ತೆ square ಆಗುತ್ತೆ. Otherwise it will become rectangle. But in the problem he has given it is a square. So because of that condition I have taken B is equal to T is equal to 30 mm. Then P, rated load is given in the problem. P is equal to 400 kilonewton. So convert this into a Newton. So 400 into 10 to the power of 3 Newton. So mu is equal to 0.25. Then capital E, that is Young's modulus. E is equal to 200 kilonewton per mm square. So this is equal to 200 into 10 to the power of 3 Newton per mm square. To find the change in the volume. To find change in the volume, so what you need to find out first, right? First you think of the formula, which formula you need to use. So there the formula is, if I write the formula as, see, now the K, that is bulk modulus K. So this bulk modulus K is equal to the sigma divided by the epsilon V. Epsilon V means what? It is the volumetric strain. So sigma and volumetric strain. right? You need to find out this volumetric strain. So by this formula, now I am calculating K. So how to calculate K? You write the relation between K and E. So that we know that the relation between K and E is equal to 3K 1 minus 2 mu. So this is Poissons ratio. Poissons ratio also is given in the problem, and E also given in the problem. Then find out K, that is bulk modulus. So K is equal to E. So keeping E this side and K here only, you bring 3 here and 1 minus 2 mu here. So E divided by 3 into 1 minus 2 mu. Substitute all the values here. So K is equal to E value given as 200 into 10 to the power of 3 divided by 3 into 1 minus 2 into 0.25. So the answer will be 1.34 into 10 to the power of 5 Newton per mm square. So this is the bulk modulus value. Later on, so find out the area. Area A is equal to B into T, because it is given in the problem is square. So the square, how to find out the area of the square? Side into side. Side, one side is B, one more side is T. So both are equal. So 30 into 30, it works out to be 900 mm square. Now find out the sigma. Sigma is equal to P by A. So that is equal to 400 into 10 to the power of 3 divided by 900. So that will be 444.44 Newton per mm square. So this is what? This is the sigma value. Then bulk modulus, write the equation for bulk modulus. So bulk modulus K is equal to direct stress by volumetric strain. So the direct stress by volumetric strain. So now you need volumetric strain. So bring volumetric strain on the left hand side and write it as epsilon V is equal to sigma divided by K. So just now you find it out at the sigma and also the K. Substitute these two values in the equation. So 444.44 divided by 1.34 into 10 to the power of 5. So that is equal to 3.31 into 10 to the power of minus 3. So this is the volumetric strain. Now find out the volume. So V is equal to B into T into L. So write it 30 into 2400. So that will be 21.6 into 10 to the power of 5 mm cube. So volumetric strain epsilon V is equal to, you know that already, how to find out the volumetric strain. Epsilon V is equal to change in volume, that is delta V. So divided by original volume, that is V. So therefore change in volume delta V, so is equal to epsilon V. So bring this original volume on this side. So epsilon V into the V, epsilon V into V, that is 3.31 to 10 to the power of minus 3 into 21.6 into 10 to the power of 5. So that is equal to 7149.6 mm cube. So this is the change in the volume. So this is asked in the problem. So in the next problem, that is the following data pertains to a tension test conducted in laboratory. See, the problem itself is one page. So you read this problem carefully. The following data pertains to a tension test conducted in laboratory. So in laboratory, first one he has given diameter of the specimen is 15 mm. Then the length of the specimen is 200 mm. Extension under a load of 10 kilonewton is 0.035 mm. Load at yield point is 110 kilonewton. Maximum load is 190 kilonewton. Length of the specimen after failure is 255 mm. Neck diameter is 12.25 mm. Right? Then what he is asking now, determine Young's modulus, yield stress, ultimate stress, percentage elongation, percentage reduction in area, safe stress, adopting factor of safety of 1.5. Right? So now I'll draw, this is the stress strain diagram, like this. This is stress strain diagram. As I told, this is O point and it comes here as the A point. So then here it comes the B point. This is B point, and at this point it is C point. Here it is D point, and here it is E point. This is E point, and this is F point. So now this is stress, y-axis is stress, and this is strain, x-axis is strain. The diameter of the specimen is 15 mm. So ನೀವು ಯಾವಾಗ ಈ ಸ್ಪೆಸಿಮೆನ್ ಅನ್ನ ಟೆಸ್ಟ್ ಮಾಡ್ಲಿಕ್ಕೆ ತಗೋತಿರೋ ಆವಾಗ ಡಯಾಮೀಟರ್ ಎಷ್ಟು ಇರುತ್ತೆ 15 mm ಇರುತ್ತೆ 15 mm ಇಟ್ ಇಸ್ ಒನ್ ರಾಡ್ ದ ಲೆಂತ್ ಈಸ್ ಆಫ್ 200 mm 200 mm ಮತ್ತು 15 mm ಡಯಾಮೀಟರ್ ಇದ್ದಂತ ಒಂದು ರಾಡ್ ಅನ್ನ ಟೆನ್ಸೈಲ್ ಟೆಸ್ಟಿಂಗ್ ಮಷೀನ್ ಅಲ್ಲಿ ಹೋಲ್ಡ್ ಮಾಡ್ತೀರಿ ಅದಕ್ಕೆ ಟೆಸ್ಟ್ ಮಾಡ್ಲಿಕ್ಕೆ ಸೊ ಆ ಟೆಸ್ಟ್ ಮಾಡ್ಲಿಕ್ಕೆ ಸ್ಟಾರ್ಟ್ ಮಾಡಿದಾಗ ಲೋಡ್ ಎಷ್ಟು ಹಾಕ್ತೀರಿ ನೀವು ಇನಿಷಿಯಲ್ ಲೋಡ್ ಇಸ್ 10 ಕಿಲೋ ನ್ಯೂಟನ್ ಸೊ ಯು ಆರ್ ಪುಟಿಂಗ್ 10 ಕಿಲೋ ನ್ಯೂಟನ್ ಸೊ 10 ಕಿಲೋ ನ್ಯೂಟನ್ ಅನ್ನ ನೀವು ಹಾಕಬೇಕಾದಾಗ ಆ ಲೆಂತ್ ಎಷ್ಟು ಇನ್ಕ್ರೀಸ್ ಆಗುತ್ತೆ ಎಕ್ಸ್ಟ್ರಾ ಅಂತಂದ್ರೆ 0.035 mm ಆಗುತ್ತೆ ಅಂತ ಹೇಳ್ತಾನೆ then load at yield point you know the yield point means c is upper yield point d is lower yield point whenever he is given it is load at yield point you consider it as c upper yield point only the c value c point ge bandaga at this c point what will be the load is 110 110 kilonewton yes 110 kilonewton irutte c point alli anta ಹೇಳ್ತಾ ಇದ್ದಾನೆ maximum load is 190 kilonewton maximum load is where at the e point it should be here it is 190 kilonewton ಇಲ್ಲಿ ಇರುತ್ತೆ e point ಅಲ್ಲಿ but at c point how much at c point it is 110 kilonewton e point ಅಲ್ಲಿ length of the specimen after failure where it fails at f point after failure what would be the length of that specimen the length will be 255 mm but what was its earlier length was 200 mm then after fracture how much increase in the length that is 55 mm increase in the length you notice the 15 mm increase in the length after fracture then neck diameter is given neck diameter is 12.25 mm neck diameter as I told initial the diameter is same after applying the load it forms the neck so that diameter from 15 mm to 12.25 mm so 15 mm ಇದ್ದಿದ್ದು ನೀವು ಟೆಸ್ಟ್ ಮಾಡ್ತಾ ಹೋದಂಗೆ ಅದರ diameter 12.25 ಆಗಿ ಲಾಸ್ಟ್ ಅಲ್ಲಿ ಏನಾಗುತ್ತೆ ಬ್ರೇಕ್ ಆಗಿಬಿಡುತ್ತೆ so the diameter is 12.25 mm at the neck diameter ಇದು ಎಲ್ಲಾ ಡೇಟಾನ ಇಟ್ಟುಕೊಂಡು ವಾಟ್ he is asking you to find out is Young's modulus yield stress ultimate stress percentage elongation percentage reduction in area safe stress adopting factor of safety 1.5 so mark this problem as very important this problem is repeatedly asked in the question paper so note it down this is important problem so now we'll start solving this first find out the original cross sectional area since the given dimension is diameter that is d so to find out the area a is equal to pi by 4 into d square so that is equal to pi by 4 into 15 square so after this you will get it the 176.7 mm square the yield stress sigma y is equal to yield load by original cross sectional area how to find out yield stress by yield load by original cross sectional area so this is same the formula like p by a sigma is what p by a the p means load a means area original cross sectional area when you are finding out yield stress you take yield load only then it will give you yield stress yield load by original cross sectional area you know that yield load is 110 kilonewton so 110 into 10 to the power of 3 it becomes in newton so divide this by the original cross sectional area that is 176.7 so you will get 622.5 newton per mm square then find out maximum stress is equal to maximum load by original cross sectional area again it is same so where the maximum load takes place the maximum load will be at the ultimate point so the load at ultimate point itself is the maximum load take the maximum load by original cross sectional area so that is equal to 190 into 10 to the power of 3 it is not 103 it is 10 to the power of 3 so 10 to the power of 3 divided by 176.7 so that will give you 1075.26 newton per mm square this is maximum stress this is the yield stress then final cross sectional area why to find out final cross sectional area because when it fractures when it breaks at that time the diameter is different so by that you can find out so final area AF is equal to pi d square by 4 this is not p this is pi again this is pi so pi into 12.25 whole square by 4 this is equal to 117.8 mm square this is the final area when it breaks So the percentage elongation, you find out percentage elongation, that is change in the length by original length into 100. So this is LF minus L naught by L naught. Change in length means the final length. This is the final length. Subtract the original length in the final length, you will get the change in length to the original length into 100. So that will give the percentage elongation. So the final length is 255 minus 200 is the initial length divided by 200 into 100, that is 27.7%. So this is the percentage elongation. Similarly, you find out the percentage reduction in area, that is change in cross-sectional area by original cross-sectional area into 100. So that is equal to A naught minus AF by A naught into 100. So this is equal to 176.7 minus 117.8 divided by 176.7 into 100. So that will be 33.3%. So this is the percentage reduction in area. Now you know that the factor of safety is given by, factor of safety is equal to yield stress by safe working stress. It is safe working stress, that is 1.5 is equal to 622.5 divided by safe working stress. And now you find out the safe working stress will go on this side, then 1.5 will come this side. So then you will find out it as, therefore safe working stress is equal to 622.5, so divided by 1.5, so that is equal to 450 Newton per mm square. The next one is stress under a load of 10 kilonewton. Now find out stress under load of 10 kilonewton, because initial load is 10 kilonewton. The stress is applied load by original cross-sectional area, so that is P by A. Substitute applied load is 10 kilonewton. So convert this into a Newton, it becomes 10,000 Newton. So original cross-sectional area is 176.7. So that is equal to 56.5 Newton per mm square. So this is the stress. Then what is the strain? Change in length by original length. Change in length is also given in the problem. That is 0.035 is change in the length. Divided by original length is 200. So that will be 0.000175. So this is the strain. There is no unit for the strain. Then find out the Young's modulus. Young's modulus, you know that it is sigma by epsilon. As per Hooke's law, it is sigma by epsilon. Sigma is 56.6 divided by 0.000175. So that will give you 3.22 into 10 to the power of 5 Newton per mm square. This is the Young's modulus. Right? We'll see the next problem. In an experiment, a steel specimen of 13 mm diameter was found to elongate 0.2 mm in a 200 mm gauge length. When it was subjected to a tensile force of 26.8 kilonewton, if the specimen was tested within the elastic range, what is the value of Young's modulus for the steel specimen? So it is again simple. Again in the problem, first you understand clearly and you note it down what is the given data. So the given data, diameter D is 13 mm, elongation delta L is 0.2 mm, then length L is 200 mm, and the force given as 26.8 kilonewton. So now let E is equal to value of Young's modulus for the steel specimen. We know that cross-sectional area of the specimen is A is equal to pi by 4 d square. So that is equal to pi by 4 into 13 square, because diameter is given in the problem is 13. Substitute the diameter value in this equation. So pi by 4 into 13 square. So the area works out to be 132.73 mm square. Similarly, elongation of the specimen delta L. Delta L is given 0.2. So it means delta L is equal to PL by AE. So right. So delta L value is given in the problem as 0.2. So substitute the value of 0.2 here. The P also given as 26.8. L is also into 20. Then divided by, so 132.73. E you keep it as it is, E. So that is equal to 40.38 divided by E. So E is equal to 40.38 divided by 0.2. So that will become 201.9 kilonewton per mm square, or 201.9 gigapascal. So this is the answer. So now similarly, next problem, problem number 8. So a hollow steel tube 3.5 meter long has external diameter of 120 mm. In order to determine the internal diameter, the tube was subjected to a tensile load of 400 kN and extension was measured to be 2 mm. If the modulus of elasticity for the tube material is 200 gigapascal, determine the internal diameter of the tube. Right? He is asking internal diameter of the tube because the given is a hollow steel tube. If it is a hollow, then it will have internal diameter as well as external diameter. So external diameter value he has given in the problem. Then he is asking you to find out the internal diameter. So again write down the given data. So given is length, L is 3.5 meter. So convert this into a mm. So 3.5 into 10 to the power of 3 mm. So external diameter D is 120 mm. Load is given as 400 kilonewton. So convert this into a Newton. So 400 into 10 to the power of 3 Newton. So then extension delta L is 2 mm. And modulus of elasticity is E is equal to 200 gigapascal. So that is equal to 200 into 10 to the power of 3 Newton per mm square. So D is equal to internal diameter of the tube in mm. Let the capital D, we have taken it for external diameter, and small d I am considering it for internal diameter. So we know that area of the tube now. A is equal to pi by 4 120 square minus d square. It means it is capital D square minus small d square. Capital D is given in the problem, that is 120 mm. So I am substituting a d here, 120 mm square minus small d square. So this is equal to 0.7854 120 square minus d square. This is the area now. So I am keeping this as it is because I need a d value. D value is unknown. So that only we need to find out in this problem. So next you write the equation for extension of the tube, that is delta L. So delta L, this 2 is again it is delta L. Delta L is equal to PL by AE. In the problem, delta L is given as 2. So 2 is equal to 400. P value is 400 into 10 to the power of 3. L value into 3.5 into 10 to the power of 3. So divided by A is you have calculated in the previous value is 0.7854. 120 square, it is not cube, it is square. 120 square minus d square, 200 into 10 to the power of 3. So this is equal to 8913 divided by 14,400 minus small d square. So this will be, this bottom one, this will be multiplied with 2, that is delta L. So it becomes 28,800 minus 2 small d square is equal to 8,913, or 2d square 28,800 minus 8,913, so that is equal to 19,887. So small d square is equal to 19,887 divided by 2, that is equal to 9,943.5, or small d is equal to 99.71 mm. So this is the value required, right? This is the internal diameter of the tube in mm. So this reference I made it, Strength of Material by R.S. Kurmi. So thank you. That is the end of the session.